Welcome to the lesson on flooded lead-acid battery. In this lesson, we will look at the history, chemistry, and construction of flooded lead-acid batteries. Let us look at our lesson objectives. By the end of the lesson, you will be able to define a flooded lead-acid battery. Next, you will be able to explain how it differs from general lead-acid batteries. Then, you will be able to describe the key historical milestones in the development of flooded lead-acid battery technology. Later, you will be able to explain the chemical processes that occur during the discharge and charging cycles of a flooded lead-acid battery. Subsequently, you will be able to identify the components and construction of flooded lead-acid battery electrodes. Finally, you will be able to describe the safety procedures when handling, maintaining, or charging flooded lead-acid batteries. While lithium-ion batteries are dominant in modern BEVs, you may encounter older vehicles that utilize different battery technologies. Knowing their history, construction, and chemistry is crucial for proper servicing. A strong foundation in battery chemistry and how different battery types function during charging and discharging will enable you to pinpoint battery health and performance issues. Understanding the safety consideration for various battery types will equip you to handle all EVs and related components safely. A well-rounded knowledge of battery history, construction, chemistry, and operation across various battery types will equip you to effectively diagnose, service, and maintain a broader range of EVs safely and efficiently. What is a flooded lead-acid battery? A flooded lead-acid battery is a specific type of lead-acid battery in which the electrolyte solution completely floods the plates within the casing. These batteries require periodic maintenance, such as topping up the water content in the electrolyte as it evaporates over time. On the other hand, a lead-acid battery is a broad category encompassing all batteries that utilize lead plates and sulfuric acid electrolytes for operation. They are a mature and well-established battery technology. Even though BEVs have a large lithium-ion battery, they typically have a 12V lead-acid battery to power essential low-voltage electronics like lights, radios, and computer systems. Understanding how to maintain or replace this 12V battery, which might be flooded or sealed, is essential for BEV technicians. Knowing the principles behind flooded lead-acid batteries, a common and relatively simple technology, provides a foundational understanding of complex lithium-ion batteries in BEVs. Let us now look at the history of flooded lead-acid batteries. In 1800, Alessandro Volta invented the voltaic pile, which is considered one of the first true batteries. It used zinc and copper plates with a brine-soaked separator but wasn't rechargeable. In 1859, Gaston Plante invented the first lead-acid battery. This early design could be recharged, but it wasn't very efficient and required significant development. In 1886, Henri Tudor started mass production of improved lead-acid batteries, making them more commercially viable. These were flooded lead-acid batteries with the electrolyte solution as a liquid. Throughout the 20th century, lead-acid battery technology continued to improve with advancements in materials and design. Sealed lead-acid batteries, like absorbed glass mat, abbreviated as AGM, and gel cell types, emerged in the late 20th century. In Volta's pile, the metals, zinc and copper, acted as conductors, allowing the electricity generated by the chemical reaction to flow across the pile and complete a circuit. Volta's pile is considered the first wet cell battery because it uses a liquid solution, brine, between the metal plates. This liquid electrolyte played a crucial role in the chemical reactions that produced electricity. Volta's invention paved the way for flooded lead-acid batteries in a few ways. The voltaic pile demonstrated that chemical reactions involving different metals could generate electricity. This concept became the foundation for further research and development of batteries. Using a liquid electrolyte in Volta's pile became a fundamental principle for many early battery designs, including the flooded lead-acid battery invented by Plante. Although Volta's invention wasn't a flooded lead-acid battery itself, it played a crucial role in laying the groundwork for their development and understanding of the principles of wet cell batteries. In a flooded lead-acid battery, the positive electrode, anode, is made of lead dioxide, PbO2, and the negative electrode, cathode, is made of sponge lead, Pb. During discharge, lead dioxide undergoes a reduction reaction, meaning it gains electrons and releases oxygen. This contributes to the flow of electricity in the circuit. Sponge lead is oxidized during discharge, meaning it loses electrons. This loss of electrons from the negative electrode is balanced by the gain of electrons at the positive electrode, creating the electric current. The spongy texture of the lead plate increases the surface area, allowing for more efficient chemical reactions during charge and discharge cycles. The electrolyte solution in a flooded lead-acid battery is a dilute sulfuric acid, chemical formula H2SO4 solution, mixed with water. This solution plays a vital role in the chemical reactions that generate electricity. The specific water ratio to sulfuric acid can vary slightly depending on the manufacturer and battery application. Typically, a fully charged lead-acid battery will have a sulfuric acid concentration of around 30% to 35% by weight, with the remaining 65% to 70% being water. When a flooded lead-acid battery discharges completely, the following occurs. All the sulfuric acid, chemical formula H2SO4, in the electrolyte gets used up. Both electrodes become coated in lead sulfate, chemical formula PbSO4. The remaining electrolyte becomes pure water, chemical formula H2O. In this state, the battery can't deliver electricity because there's no more sulfuric acid for the chemical reactions. Charging essentially reverses the process that happens during discharge. Sulfate ions, SO4, move from the electrodes back to the electrolyte. Lead sulfate is converted back to lead dioxide, chemical formula PbO2, using energy from the charger and water from the electrolyte. No direct oxygen involvement. Electrons from the charger convert lead sulfate back to sponge lead, chemical symbol Pb. Water breakdown during charging creates hydrogen gas, H2, that needs to be vented from the battery. Flooded lead-acid batteries rely on a simple but effective electrode design. The foundation of each electrode is a grid structure cast from a lead alloy. This grid provides essential mechanical support for the active material that will be applied later. Imagine a miniature lattice made of lead alloy. That's the grid. The lead alloy grid isn't enough for the battery to function. A paste containing lead oxides is then applied to the grid. These lead oxides are the key players in the chemical reactions that generate electricity during discharge and recharge cycles. Think of the paste as the fuel for the battery's operation. Lead antimony, brittle metal, grids made primarily of lead, Pb, with added antimony, Sb, are prone to gassing, causing water loss over time due to electrolysis. Antimony, OSB, is a metallic element that is often used in combination with other metals to improve their properties. In the context of lead-acid batteries, it is added to lead to form lead-antimony grids. These batteries use calcium, Ca, in the grid alloy to reduce gassing, minimizing water loss and maintenance requirements compared to traditional lead antimony grids. Flooded lead-acid battery electrodes are made with a lead alloy grid for support. A paste containing lead oxides is then applied to the grid. This paste reacts with the electrolyte during discharge and recharge. Traditionally, lead antimony grids caused excessive gassing, water breakdown during charging, leading to water loss and maintenance needs. Modern batteries use calcium or less antimony, brittle metal, in the grid to significantly reduce gassing, making them lower maintenance. Flooded lead-acid batteries aren't single units, but rather a collection of cells working together. Imagine a box divided into sections, each section holding a mini battery, cell. These mini batteries are connected by straps that go through walls separating the sections. This allows them to act like one bigger battery with higher voltage. Let us now look at the safety precautions for flooded lead-acid batteries. Firstly, let us focus on the do's. Secure the cell covers while charging to prevent sparks and spills. Connect the charger to the battery before plugging it in to minimize sparking risk. Wear appropriate personal protective equipment, abbreviated as PPE, like gloves, face shields, and safety clothing when handling the battery's corrosive acid. Utilize a lifting device for heavy batteries to avoid injury. Maintain proper hold down for secure battery placement during transport. Only add distilled water to the battery cells to maintain electrolyte levels. Regularly clean the battery case and terminals to ensure optimal performance. Let us now look at the do-nots. Do not create sparks near the battery, especially during charging. Avoid overcharging the battery and reduce the charging rate if the case gets too hot. There are several advantages of lead-acid batteries. Lead and sulfur, the key components, are relatively inexpensive. The straightforward design and production process contribute to lower costs. It provides sufficient power for starting a car and similar applications. A well-established infrastructure allows for the recycling of 97% of lead-acid batteries, making them an environmentally friendly choice. Let us look at our lesson summary on flooded lead-acid battery. Flooded lead-acid batteries are a type of lead-acid battery where plates are submerged in a liquid sulfuric acid electrolyte, requiring regular maintenance. They operate based on chemical reactions between lead dioxide and sponge lead with sulfuric acid, creating an electric current. Historical development began with Volta's pile in 1800, advancing with Planck's rechargeable battery in 1859 and Tudor's commercial improvements in 1886. Electrode construction involves a lead alloy grid and a paste of lead oxides. Alloy compositions like lead antimony or lead calcium influence gassing and maintenance needs. Proper safety practices, such as using personal protective equipment and avoiding sparks during charging, are essential to prevent accidents and battery damage. Thank you.